Welcome to homework.
This question is in reference to binding energy. In order to calculate binding energy, you first need to figure out the mass of the nuclide. Knowing the mass, the summed mass of the nuclide from its summed parts, protons, neutrons, and electrons, you can calculate the mass defect by subtracting it from the actual mass of the nuclide. Then, once you have the mass defect, you can use the Einstein equation, E equals mc squared, in order to calculate the energy associated with the formation of that particular nuclide, or the energy you would have to add in order to break that nuclide apart into its constituent protons, neutrons, and electrons. Once you know the binding energy per nuclide, you can calculate the binding energy per nucleon by dividing by the number of nucleons that are present in that particular nuclide. So let's get started. For the first nuclide, we have nitrogen-14. Nitrogen contains 7 protons, so we will start by calculating the summed mass of 7 protons. 7 times, this is the mass of a single proton in kilograms, which you can look up. It also contains 7 neutrons. The mass of a neutron is slightly greater than the mass of a proton, and so you'll notice this number is just a little bit larger than this number. It also contains 7 electrons, so we'll add in the 7 electrons. This will then be the summed mass of a single nuclide of nitrogen-14. We'll subtract that from the mass of the measured mass of a nitrogen-14 nuclide using instrumentation. This is 13.999234 AMU. Or you could assume that this same number is the mass in grams of a mole of those nuclides, which is what I did. There's several ways to get to the mass of the single nuclide. So I'll start with that number provided in grams per mole, convert the moles into number of nuclides by dividing by Avogadro's number, and then I will have the mass per single nuclide instead of mole of nuclides, and then I'll convert it from grams to kilograms so my units match up here. And then I'll subtract these two numbers. So this is the actual mass of a carbon-14 nuclide. This is the summed mass of a carbon-14 nuclide. The difference is what we call the mass defect. If you chose to carry out the calculation of this minus this, you'll get a negative number, and some people prefer to do that, recognizing that this is a defect, a loss of mass. The binding energy then can be calculated using E equals mc squared. So m will be the mass of the nuclide we just calculated, the mass defect of the nuclide we just calculated, multiplied by c, which is the speed of light, 2.9979 times 10 to the 8 meters per second squared. This will then give us units of joules. It'll be joules per nuclide. If we want joules per nucleon, then we need to recognize in nitrogen-14 there are 14 nucleons. So we divide that by 14, and we get 1.235 times 10 to the negative 12 joules per nucleon. And again, some people prefer to put negative signs here in order to emphasize that this is energy released during the formation. Now let's go to the next one, titanium-48. Titanium-48 has 22 protons, because all titanium nuclides have 22. In order to figure out the number of neutrons, it'll be 48 minus 22, which gives us 26, multiplied by the mass of a neutron. And then because it's an atom, it has the same number of electrons as protons, so it has 22 electrons. This will then be the summed mass of a titanium-48 nuclide in kilograms. We need to now subtract that from the measured mass of a uranium-48 nuclide, which was provided, 47.935878 grams per mole, or 47.935878 AMU. Our objective is to get to units of kilograms, so I'm just going to assume that this is the same mass in grams per mole as we had AMU, and then divide by Avogadro's number, so we now have grams per nuclide, and then divide by 1,000 so that we have kilograms per nuclide. Then we'll subtract the actual mass, or subtract the summed mass from the actual mass, in order to get the mass defect. 7.6464 times 10 to the negative 8 kilograms. This is now the mass defect. And again, some people prefer to put a negative sign here and carry out the calculation to emphasize that this is a loss of mass. If we then take this value and put it into the Einstein equation, E equals m, the mass defect, multiplied by the speed of light squared, we'll get units of joules, 6.872 times 10 to the negative 11 joules. This is joules released per formation of one titanium-48 nuclide. If we want to determine the joules per nucleon, we'll divide that by the number of nucleons in titanium, which is its mass number, 48. And we'll get 1.432 times 10 to the negative 12 joules per nucleon. The last one now is xenon-129. Xenon has 54 protons. So we'll first start again with the calculated mass, 54 times the mass of a proton, plus 54, or 129 minus 54 gives us the number of neutrons, 75. So 75 times the mass of a single neutron, plus we also have 54 electrons, 54 times the mass of an electron. This gives us the summed mass from the mass of its parts of a xenon-129 nuclide. We'll then convert the measured mass, which was given to us as 128.90479 AMU. We'll write that as grams per mole, convert the grams per mole to grams per nuclide by dividing by Avogadro's number, and then go from grams per nuclide to kilograms per nuclide by dividing by 1,000. This then is the actual or measured mass minus the summed mass, gives us 1.93406 times 10 to the negative 27 kilograms as our mass defect. We're then going to take the mass, oftentimes represented as a negative number, which I think I've tried to be consistent here. The way I've set it up, we get negative values. I guess that one's, whoops, yeah, that one's negative, and this one's negative. Multiply that mass by the speed of light squared in order to get the joules per nuclide that are released. And again, typically people like to put a negative sign here to emphasize that it was energy that's released. This is the energy released per nuclide in joules. To get the energy released per nucleon, we need to divide by the number of nucleons that are present in xenon-129, which is its mass number 29, and we get 1.347 times 10 to the negative 12 joules per nucleon. And this is kind of what we expect. We see an increase in the joules per nucleon as we go to greater and greater atomic masses until we get to iron 56, which would come somewhere right after titanium-48, and then we see a drop off, 1.432 to 1.347.